Good afternoon, this is Mr. Schweitzer, and we're going to do a little video here today on percent composition and empirical formulas and molecular formulas. So, get to the right video here. Okay. And I kind of consider this to be a little bit of an alternate method. So we're going to start out this thing again. Our topics here are going to be percent composition. It's going to eventually lead into topics of empirical and molecular formulas. And it's a little bit different way than maybe I would normally teach it, but just kind of want to show a different way so that if the old way doesn't make sense, or if you truly understand something, then this would be a very understandable way as well. Before we start anything, let's just take a chemical, let's say like P4O10. And I'm going to make a couple just generalizations that if you have one of these guys, then you're going to get 4 phosphoruses and you're going to get 10 oxygens. If you have 2 of these guys, then you would get 8 phosphoruses and you would get 20 oxygens. If you have 100 of these guys, you would get 400 and looks like about 1,000 here. So this ratio of phosphoruses to oxygens is locked at 4:10 ratio based on the molecule. So here's a thought. If you have 1 mole of phosphorus, P4O10, and that particular in that sense, okay, how many phosphoruses would you get? Well, you would get a bunch of phosphoruses, but you keep it in moles, you get 4 moles of this guy, and you would get 10 moles of this guy. So keep that concept in mind here. Now, 1 mole of phosphorus, how much does 1 mole of phosphorus weigh? Well, doing the molar mass of phosphorus weighs 30.97, and there are 4 of them. And I'll just be calculating along with it. 30.97 times 4, 123. We'll go 0.8. And oxygen wise, there's 10 of them, and each of those weighing, let's just say 16, for 660.0 grams here and grams here, for a grand total of 283.8. And this would be grams per 1 mole, and that's really how much the 1 mole weighed. So in this case, if we were to take 283 grams, 0.8, let's do a 0.8 on there, of P4O10, and we were to break this down into how much phosphorus, how much oxygen, we should get this same ratio, 4 moles and 10 moles. I'm going to do this 2 ways. One way, just so you realize it this way, is I'm going to do the percent mass phosphorus first, percent mass oxygen. A little side here just so we have it. To get the percent mass phosphorus, I'm going to take the 123.8 divided by the total, 123.8 divided by the 283.8 times 100, gives me about 43.6%. 43.6%. And if I take the other one, 160.0 divided by 283.8 times 100 equals 56.3%. Now I'll get pretty close to 100% here. Now, the old method for this to go from a percent mass to a formula would be to, I'm just going to paraphrase this for a second. You might be new, this might be the first time you've seen this, so it may not mean as much to you. But I want to go from a percent mass to an empirical formula, which is a ratio of individuals. So I want to take and do by percentage by mass, and the general method is take your percent by mass and convert it to grams. So you need to set a sample size, and typically that sample size is 100 grams, and then you would say grams into moles. This is the number of moles in your sample size, and then you would divide out by the smallest one. That sets your smallest one to 1, and it basically makes your formula empirical. Divide by smallest. This is empirical. Alright. At this point, okay, that is typically the way we would do it. And I can do this right here, and I'd say, okay, well, if I have percentage, let's set my sample size at 100 grams. And this is my more standard method of doing it. I would get 43.6 grams and 56.3 grams. That's in a 100 gram sample. Take your 100 grams, multiply by 0.436, and you get your grams of that sample in that sample size. This is the amount of grams in a 100 gram sample of that individual piece. Then I want to go to moles. Okay, so get rid of grams and go to moles. Get rid of grams and go to moles. Now, again, I only have 100 grams. So how many moles are there in 100 grams? There's some decimal fractional amount. So 1 mole equals, for phosphorus, 30.97. We would never expect it to come out to a whole number of moles. I mean, 100 grams is just basically some random number of particles, so I would expect to get some decimal. So when I take the 43.6 divided by 30.97, I get, again, 1.40 moles. And this guy, 56.3 divided by 16 equals 3.51. Again, this is just some decimal. This is the number of moles in this random sample. Again, I would never expect that it would come out to be 2, 3, 4, 5, some nice whole number, because I just have some random sample size. Now, the next step would be to divide by the smallest amount here, by the smallest number. So this sets my smallest one to 1, which is 1.40, and 1.40 gives me 1, and let's take 3.5 divided by 1.4, and it ends up being identically 2.5. Now, in this case, because I have my empirical formula P1O2.5, or 2.5, you really can't have half an oxygen atom. So what we do is we do one last step and we multiply by the reciprocal. Okay, this gives me the reciprocal of times 2 times 2 gives me P2O. In this case, 2.5 times this guy would be P2O5. And there we go. And this is my empirical formula. Okay, P2O5. Now, just empirical, not necessarily my molecular. Again, to flip, very important to go from a empirical formula to a molecular formula. I would need one piece of information as my molecular weight, which is going to be 283. take this thing here, has an empirical weight, and if you add everything up, phosphorus is 30.97 times 2 is awfully close to 72. 30.97 times 2, of close to 62. This is going to be 61.94. 61.94. The oxygen is going to be 16 times 5, which gives me 80. And then it's okay, well, 80 plus the 61.94 is 141. So my empirical weight is 141.94. Now I would expect my actual formula to be some multiple of that, and the actual weight is 283. My smallest, simplest percentage is 141, and you'll say that comes awfully close to 2. So my actual formula is 2 times that. And 2 times that would give me P4O10. Now, let's backtrack a little bit here and see how that's different than what if, okay, I were to choose a sample size that wasn't random. Now 100 grams is nice only legitimately for the very first step. It allows you to make your 43.6 your actual 46.3 grams. What if we chose one that was a little more precise? Let's take this 283 for example. We do know that 283 is the mass of 1 mole. And we do know that in a mole there should be 4 phosphoruses and 10 oxygens, mole-wise. Let's try that math once and see how it works out. Now, in this case, I'm going to give myself a little more room here. I was going to do it right there, but I'll do it right here. So I have 283 grams, 283.8 grams. And I'm going to follow the same procedure. I'm just going to flip them to moles. Alright, dot line, get rid of, well, I want to go to the percentages. So of this guy, this is the whole thing weighs this amount. So let's go, again, I have 43.6% of this thing is due to phosphorus. And in this case, I have 56.3% oxygen. Now again, I may not know that this thing is P2O5 or that the actual is P4O10. This is not knowledge that you have. You know that the thing weighs this much, 283, and that these are the percentages. Okay, so let's, rather than using 100, let's use this guy. Okay, so times, so get this thing into grams. So I'm going to go from percentage to grams. Okay, so 0.436 times 283.8. And this gives me 283.8 times 0.436 equals 123.7 grams of phosphorus, and 0.563 percentage times 283.8 grams. Keep in mind that's a percent by mass, and that's a mass. All right, well, this works. 283.8 times 0.563 equals 159.7 grams of the oxygen. Alright, let's do the next step, convert to moles. Now again, the last one we got these random sizes of moles. But this time, because I picked a very specific number of moles, I'm thinking my moles will come out to a whole number. Because I have 1 mole of this stuff that I picked, so therefore I should get, if I have 1 mole of this, I should get 4 moles of phosphorus and 10 moles of oxygen. based on its formula, without even knowing that that's my formula. So dot line, get rid of the grams, and go to moles. 1 mole is 30.97. And dot line, get rid of grams, and go to moles. 1 mole is 16. Let's try this out. 123.7 divided by 30.97 equals 3.99. 3.99. Of course, I'm using this, I'm expecting a whole number, approximately 4. And this guy is 159.7 equals 159.7 divided by 16 equals 9.9, approximately 10. So this time all I did was convert to moles, and rather than it falling on some random number, it fell to the actual number of moles in the actual compound. So now that's my molecular formula, P4O10. If I continue to the next step of dividing, this just determines, again, just like the last problem, it sets my smallest one-to-one, or creates an empirical formula. And I would just simply, well, I shouldn't say that. I can't really reduce this. I can't really divide here, I guess I should say. I'm just going to, rather than divide, I am going to reduce. Okay? This reduces down to 2 and 5. Easy enough to do. Just common lowest multiple there. And my empirical is P2O5. This is another option of choosing another means by which to starting mass to get to your answer. So you don't always given this original mass, but if you did, sometimes it's helpful to use the more mass instead. Thank you very much.